Hi, everyone. I'm the first session of the afternoon today. Thanks for the great workshop so far to all the organizers. I've really enjoyed having lots of conversations with people already. So as Georgia nicely introduced, I'm based at Yale. I'm here to talk about work that I've done with my collaborator, Chi-Lo Su, and my advisor, Shruti Puri. And we're going to show how teleportation, which is a key subroutine in measurement-based error correction, can decohere errors. Okay, so let's start with the motivation. What do we mean by decohering errors and why we would want to do that? So first, let's revisit basic assumptions about noise in the context of quantum error correction. Typically, when we study quantum error correcting codes, we assume poly errors, where each qubit has some stochastic probability to experience a poly X, Y, or Z error. And here's a simple example of a poly channel where this qubit has some probability PZ to have a Z error. So poly error models are really nice. They're very well studied in this community, and they're a great model for theory because you can simulate the performance of a quantum error correcting code with just Clifford plus poly circuit simulators, which can be done efficiently on classical computers. But in general, it's very rare that you actually get poly errors in hardware. In fact, a more physically motivated noise model to study is coherent errors, where your qubit has some unitary error acting on it. So for example, one coherent error is eta I theta z. If you were to expand this channel out, a key hallmark of a coherent error is that it has these off-diagonal terms. That's like I rho z and 0 I, where the polys conjugating the density matrix are differ. And you also have these diagonal terms, I rho I and 0 z, that also appear in the poly channel form as well. So these coherent errors are very physically motivated in atomic systems where your gates are limited by technical noise. For example, if you were to try to apply some sort of pulse to rotate your qubit, there can be timing errors that result in under or over rotations. So what is the big deal, and why do we want to study these errors is kind of what I hope to motivate very shortly. In this talk, we'll be focusing on coherent errors, but I also want to give the quick disclaimer that our work also applies to other non-poly errors within the physical qubit computational space, like the no-jump operator from amplitude damping channel, which is very common in superconducting qubits, where your qubit will decay from the E to the G state, and also the no-jump operator in biased erasure conversion in neutral atoms. So just let's focus on unitary noise for now. Even with the conventional QEC wisdom of discretization of errors, performance under coherent errors is still less understood than poly errors. And in fact, you can still get these effects that result in kind of unwanted effects compared to what you would get if you truly had poly errors in your system. I mean, one example of how we just don't understand how QEC codes work with coherent errors is the fact that even with a very simple noise model that's eta I theta z uniformly on every data qubit, we don't have a constant threshold theorem. When you have physical coherent errors on every qubit and you measure all of the stabilizers, even after discretization of errors, you still have a remaining logical coherent error, which can constructively add over many rounds of quantum error correction. Additionally, there have been numerical studies that have shown large differences in the logical error rates for polyphysical noise and coherent physical noise. And these numerical studies are kind of inconvenient to do because, in general, unless you have some efficient mapping of the coherent noise to some other physical system, these simulations grow exponentially with the system size because you're essentially doing a quantum state vector simulation. Okay, so with all of these kind of not guarantees on QEC performance with coherent errors, the other conventional wisdom is that in experiment you could do a protocol called randomized compiling to take your coherent errors and twirl them or turn them into poly errors. And so just just remember randomized compiling. I'll bring it up later. But I also want to add the disclaimer that randomized compiling isn't necessarily some theoretical tool that you should assume you can always get for free, because this also may involve doing some extra gates in order to randomize compile, or having more gates in your native gate set in order to actually do this randomized compiling. And so basically in this talk, we're going to address all of these challenges in teleportation-based error correction or measurement-based error correction. And what we'll see is that there is inherent decoherence of coherent errors in teleportation-based error correction that you just get for free. You don't even have to worry about randomized compiling, which is really nice. OK, so before I begin, I just want to give some examples explicitly of the challenges of coherent errors and what really sets them apart from your traditional stochastic poly error. And the first of the two challenges that I'll talk about is this logical coherent error, which I mentioned in the slide before, which is despite discretization of errors, logical coherent errors persist. So let's take a simple example of a repetition 3 code where your stabilizers are x1, x2, x2, x3. And if I were to put a coherent error on every physical qubit in this code, then my state after these coherent errors, if I were to just expand it all out, would be the following. And then if I go and measure the stabilizers, perfectly by the way, and I measure +1, +1 for S1 and S2, then basically the only terms that survive are going to be the terms that commute with both of my stabilizers. So it's going to be I1, I2, I3, and Z1, Z2, Z3, which in other words is I logical and Z logical. And so what I'm left with here is a logical coherent error after my stabilizer measurement. And even if I were to go and measure the stabilizers again, there's no chance of me detecting this error because it commutes with all of the stabilizers. So something I do want to mention, though, is if we had a larger repetition code, like a repetition D code, then basically the size of this logical coherent error decreases exponentially. You can see this because the sine cube theta would now go to sine to D. But for finite size codes, this logical coherence isn't necessarily going to vanish. All right, so there's this logical coherent error that isn't present in polynoise. The other key feature of coherent errors is that they add constructively, leading to faster error growth. And this is all just to say that they're unitary errors. So if I have a coherent error channel, like this e to I theta z, and my input state is plus, I'm also going to assume that my theta is small, assuming that my coherent errors are small. I've done everything I can, like my dynamical decoupling, to basically minimize this as much as I can. What I'm going to do is I'm going to take this channel and I'm going to compose it t times, and I'm going to get what the expectation value of the x is at the end of this. It should be 1 in the absence of errors. And so basically anything deviating from that is going to be my leading error term. And so just by writing out the expectation value, you can see that the error term is proportional to t squared. So t here I'm thinking of as the number of time steps, the number of channels I'm composing. And so if you were to plot the expectation value with the total number of time steps, then you can clearly see that this is a quadratic growth in errors. If I took a poly channel with the same average fidelity as my coherent error channel, so this poly channel has probability of z error with theta squared, and then I composed this many times and got the expectation value out, then my error term is linear with t, which is the key difference between the growth of errors with coherent errors versus poly errors. And so basically, you can see that the errors are not growing nearly as fast thanks to this linear growth of errors. All right, so you can probably surmise that if you have logical coherent errors after your stabilizer measurement and you're never going to get rid of them, they can potentially add constructively where each of your t's is actually a round of stabilizer measurement and error correction. So yeah, this is something we don't really want. OK, so in this work, we're going to aim to expand our theoretical understanding of coherent errors in measurement-based error correction. And we're going to try and address a lot of the problems that I motivated at the beginning. So first, we're going to see how teleportation, we're going to look at a one-dimensional cluster state or a teleportation chain, can twirl the noise into Pauli errors. And then we'll look at measurement-based error correction, or MBEC, and see that logical coherent errors will not add constructively over many rounds of error correction. And then, finally, once we start looking at some more circuit-level physically relevant errors, we'll be able to see that these errors exactly map to Pauli errors. OK, but first, let's talk about how teleportation can decohere errors. So let's take a teleportation chain where we have an input state psi that we're going to teleport over and over again. So here is the teleportation circuit. Basically, you bring in a new qubit initialized in the plus state, you do a CZ entangling gate, and then you measure the old qubit out in the x basis. And that measurement outcome is completely random. M0 is going to be 0 or 1 with 50 probability each. And basically, up to alternating Hadamard's at the end, which I'm going to ignore just for simplicity, the state that you have at the end of this teleportation circuit is the state psi up to a random z. And that z depends on the measurement outcome that you've got. Then if you teleport again, basically each one of these circuits kind of applies a Hadamard, so it swaps the role of the x and z axis. What you're going to get now is a random x up to the measurement outcome, m1. And so I could keep on teleporting my state over and over again. And what I get at the end of the day is a Pauli frame up to all the random measurement outcomes that came before it. And if I wanted to recover my state psi, then I would need to do a Pauli frame correction, which is just applying that operator in green to get back to psi. So the thing that we are interested in is if this teleportation chain has errors, what is the effective error channel on my state psi? So a simpler way of diagrammatically representing this, so I don't have to draw the circuit out every time, is we have an input state psi, and then a random z up to some random measurement outcome m0. And here we're saying our Pauli frame at time t equals 0 is z to the m0. Then we have some error, which can be a coherent error. Then we have a random x, and then an error again. And so I can just keep on repeating this pattern over and over again, however many times I would like to teleport my state. And so for those of you who are familiar with randomized compiling, you might be thinking, OK, I see random Paulis. Is this related to randomized compiling in any way? The answer is yes. I'm going to get the rest of the room caught up to speed for a little bit first. It is a little different. I do want to point out this fact. So the Pauli frames at adjacent time steps are not completely independent. They're actually correlated. For example, the Pauli frame at t equals to 1 is different from the Pauli frame at t equals to 0 by at most a random x, and not the full set of Paulis, which is described by x and z. All right, so that's an important little detail. So what is randomized compiling? So randomized compiling, as I mentioned earlier, is a technique to twirl or convert non-Pauli errors into Pauli errors. Basically, what you do is you have your noise, which you want to twirl, and you sandwich it between Pauli gates that you choose randomly in order to get an effective Pauli channel. So you would have your state that has some error channel E, and then these PIs would be randomly chosen over the full set of Paulis with uniform probability. And this would twirl E into effectively a Pauli channel. What that means is that I'm only going to take the diagonal elements of the channel, and I'm going to throw out all the off-diagonal terms. So basically, as I alluded to earlier, randomized compiling at every error source E is actually not in general equal to averaging over all these random bit MIs in the teleportation channel. Yeah?
Sorry. Do you choose a different PI for each of the T repetitions? Or
Yes.
Yeah. Okay.
Thanks for the question. Yeah, so in general, randomized compiling isn't going to be the same as averaging over these bits because of the correlated frames, as I mentioned earlier. But we're going to see that basically teleportation introduces this reduced version of twirling that will still decohere errors and still allows us to draw all these nice conclusions about quantum error correction performance with coherent errors and measurement-based error correction. Okay, so are there any questions? Okay. All right, so let's go through a simple example of how teleportation can decohere your noise. And for this example, I'm just going to look at Z rotational errors. So let's say I have a teleportation chain where first I get a random x, and then I have some e to the I theta naught z error, and then a random z, and a e to the I theta 1 z error. So I've just denote theta naught and theta 1 because they can be different in general. And I'm only going to take a short chain just for the purposes of this demonstration. So I'm going to do my polyframe correction after 2 time steps. So what I can do here is my z to the m1 is just a z operator, so I can commute it through that e to the I theta 1 error without changing anything. And when I move it past the x, I basically get a global phase. But in the context of channels, this doesn't really matter. So I can just move that across for free and cancel it out with a z in the frame correction. What I'm left with is these 2 coherent errors next to each other, which add coherently into e to the I theta naught plus theta 1 z. OK. So now if I move this x across this error, what it's going to do is it's going to flip the sign of the exponent depending on m naught. So if x was actually there, then I flip the sign. If x was not there, then nothing happens. So basically, the operator I have is e to the I minus 1 to the m naught, where m naught is 0 or 1 with 50% probability each. OK, so just writing out the channel of what this is, with half probability, m naught is 0, and then I don't flip the sign. With half probability, m naught is 1, I do flip the sign. And if I expand this out in cosines and sines and cancel all the terms, then what I should be left with is a polychannel where basically I have cosine squared theta naught plus theta 1, I rho I sine squared theta naught plus theta 1 0 z. This is the same as if I've just twirled the product of these 2 errors together. And you can do the same exercise resulting in polychannels for e to the I theta x and e to the I theta y. These result in these really nice analytical polychannels that you can just write down. And so for these cardinal axis rotations in the teleportation channel, this is exactly equal to just a multiplication of local polychannels. So what I mean by that is if I made this chain bigger, to write down the exact channel of the teleportation chain, all I would need to do is take this polychannel and compose it over many times. And each of these polychannels is only going to be dependent on my errors t and t minus 1. And so we saw earlier that when we composed many polychannels together, we got this linear decay of the fidelity. And so because we can write down these teleportation channels as a multiplication of local polychannels, we can conclude that this will result in a linear decay of your fidelity. OK, so I have verbally said what we expect, but let's actually see it plotted. So with no teleportation, my e to I theta z's add coherently. And I get this quadratic growth of errors, unsurprisingly. I've just chosen a small theta for this demonstration. If I include teleportation now, you can see that this black curve is clearly linear with the number of time steps. So we have successfully done what we set out to do, which is to go from quadratic error growth to linear error growth. Now, if I randomized compiled every error at each time t, I would get this red curve. You can see that the errors grow slower. And that's just because this random z, when you move across the error, commutes, it doesn't do anything. And so you're still allowing for some coherent interference between some local time steps. So this is an example where twirling with teleportation is not equal to randomized. Yeah?
Just a quick question. Is that about double the?
Yeah.
Okay.
Spoiler. No, you're good. Yeah, so this is an example where twirling with teleportation is not equal to randomized compiling. Now, if I were to randomize compiling once every 2 time steps, as Nick suggested, then, and I put a random poly error every 2 time steps, in the purple here, you can see that it lines up exactly on top of the teleportation as expected. All right. So I showed an example where twirling with teleportation is not equal to randomized compiling, but sometimes they do coincide. And so I alluded to the fact that because the z doesn't anticommute with the axis of the rotation and doesn't flip the sign, that's why we had this coherent interference. So if I chose eta I theta y instead, I shouldn't have this problem. So here is the coherent evolution of eta I theta y. Here is the curve for teleportation, and right on top of it is randomized compiling. And that's just because the y anticommutes with both the random x and the z that you get on the alternate steps of the teleportation. Okay. Yeah. So all this to say, we can see numerically linear decay, which means there's minimal constructive interference between errors at different time steps. Now we want to say something beyond just these nice errors we can write down analytical forms for. For general coherent errors about arbitrary axes, can we analytically guarantee that the channel will always be linear in its growth of errors? Okay. So now let's look at arbitrary axis coherent errors. So here I have my errors et as having some component of theta in the x, y, and z direction. In general, my e's can be different at every time step. Essentially, it turns out that you can't write this as exactly a multiplication of local polychannels, but you can get somewhat close. And my goal is to basically give the intuition for our result, which we have rigorously proven that for errors where coherences are small, you can still recover an effective polychannel that approximates the true channel. Okay, so basically, the intuition behind this is we know that the polyframe basically alternates accumulating a random x or z for every time step. But every 2 time steps, a full random poly is generated. And so this full random poly, as earlier, is somewhat similar to randomizing, compiling every 2 time steps. And it turns out that this is actually enough randomization to decohere errors in the chain. Some intuition that you can glean from this is that you don't really want the coherences to grow faster than the time it takes for you to accumulate a full poly. So that basically means our small coherence condition, which is that you don't want your thetas to be too large. Specifically, if you can write any channel in this form, E rho ET dagger, where I have decomposed this channel into different parts, where P is the poly part of the channel, which is all the diagonal terms, and X, Y, and Z are all the off-diagonal terms, so the coherent part of the channel, then what I'm saying essentially is that the small coherence condition is that the poly part, P of T, is order 1, and then my X, Y, and Z part of the channel is all order epsilon. So to more rigorously define what we mean by enough randomization to decohere errors, just to reiterate, this is when our true channel is approximately a composition of polychannels, which means that our noise is decohered. And so what we show is that for these small coherences, the true channel is approximated by a composition of polychannels up to order epsilon to the 4th. We can actually change how tight these bounds are, but we just wrote it down for this specific. I'm going to plot this bound in the subsequent plots. Okay, so now basically we have a way of approximating the effective polychannel of any general coherent error in the teleportation chain. And so here I'm just plotting the evolution of some axis that has components in x, y, and z. And here in blue, we have our analytical bounds that are accurate up to epsilon to the 4th. And then red is the randomized compiling if I randomized compiled every e to the I theta x, y, and z error individually. So we can see that these analytical bounds are linear. So that means that our teleportation channel, which lies in these bounds, is guaranteed to have linear growth. OK, so I mentioned that these bounds work better when your coherences are small. So if I were to plot a bigger angle, then you can see that the bounds start to widen. But the main point is that we can see that the inherent randomness of the teleportation decoheres errors into an effective poly channel. And these blue bounds are enough to say something about the linear growth of errors with the length of the chain. OK. So for these errors, I was plotting the same ET at every time step, but we can also bound errors that differ over time as well. So for this example, I'm keeping the axis constant, but then varying the theta twice, so this kind of piecewise constant axis. And we can see that the bounds still follow the teleportation chain very nicely. The intuitive reason for why the bounds still follow is that the effective polychannel that we're composing is dependent on the local time window of the errors. So more errors in more recent time steps matter more than errors in further time steps. And so that's why even when we change the errors over time, we can still bound them. And so for this one, basically, we're fluctuating the angle of theta x, theta y, and theta z in this expression, where all these deltas are uniformly chosen around 0. And once again, our bounds are still following the teleportation effective channel. So all of this to say, basically, that the actual channel can be well approximated by a bunch of local polychannels, even when errors differ over time, which is going to be useful later. OK, so now we've shown that teleportation can decohere noise in this one-dimensional cluster state. And we have successfully shown that given small coherences, errors will grow linearly instead of quadratically. Now we're going to switch focus to measurement-based error correction and see that now logical coherent errors will not constructively interfere over many rounds of error correction. OK, so let me give a quick primer on MBEC. I know it was mentioned yesterday, but measurement-based error correction in the context we're interested in looking at it in is when it foliates a stabilizer code into a many-body entangled state called a cluster state. And this cluster state can be interpreted as the teleportation of a logical qubit. OK, so here is an example of a cluster state, the RHG lattice, which is just the teleportation of the surface code. So you can see that each of these green rectangles is about a 2D slice of a surface code that's being teleported in one of the directions of space. So this cluster state is equivalent to a foliation circuit where you have an input CSS code state on n qubits, and then you act CZ gates transversely onto other n qubits initialized in the plus state, and then you measure all of the qubits out in the x spaces down here. So basically what you're doing is teleporting all of the qubits. And then you measure stabilizers. So here, I recall that the teleportation circuit changes the effect of the x and z axis. So we're able to measure these SX stabilizers with CZ gates. So we measure the x stabilizers, and then you teleport all the qubits again, and then you measure the z stabilizers. So this foliation circuit is equivalent to the cluster state picture. And this foliation circuit can also be viewed as just the teleportation of logical qubits. If you just push all the stabilizers to the beginning of the wire, then you can view this as preparing a logical state at the beginning. And this is just the single qubit teleportation chain, but now everything is promoted to the logical level. And so it's not too surprising that we should expect to use these random z logicals that we get from this Canil error correction in order to decohere the logical level coherence. So every time you teleport, you're going to get either a random logical z or a random logical x. So let's revisit some of the challenges of coherent errors that I mentioned at the beginning. The specific challenge that we want to tackle for this result is that logical coherent errors in circuit-based error correction can constructively add over many rounds of quantum error correction. And so now we're going to try to address this in MBEC and say that this is actually not a problem. OK, so how do we show that logical coherent errors do not add constructively in measurement-based error correction? So to see this, let's just take our foliation or our Canil error correction where we have an input code state psi, and our first teleportation puts a bunch of random z's on all of our n physical qubits, and then we have errors on all our n qubits as well. So I'm just putting E1 for all of them, but they can be different in general. And then we measure the x stabilizers. Then when we teleport again, we get random x's, we get some errors, and then we measure the z stabilizers. So the first thing to do is to factor out logical operators from each n-qubit poly operator. So for example, these random z's and these random x's are actually n-qubit polys. But what I can do is factor out a random z logical and a random x logical. So now basically the z to the C1 vector is still acting on n qubits, but now it's going over 2 to the n minus 1 possible bit strings. So I can just factor out these logical operators from these random polys. And if I were to try and make a single qubit teleportation-like diagram, but at the logical level, what I would do is I would have my random z logical, and then everything in the red I'm going to reinterpret as E1. And then I have a random x logical, and then everything in the red over here is going to be reinterpreted as E2. Yeah?
So just so I understand your notation, the m
Yeah.
sub 0 and the C1 vector,
Yeah.
they're just some linear combinations of the bits Mij that you've gotten from so they're just, I can infer M0 from
Exactly.
all those.
Yeah.
all those
You can map to and from them. Yeah.
And it's like a n bit to n bit.
Yes, exactly. N bit to n bit. We're just like relabeling in order to see this more clearly. Yeah. So E1 and E2, I'm also going to factor out logical operators. Basically, what I want to write E1 in the form as, for example, is I logical times some operator alpha plus x logical times some operator beta, et cetera. And we can define these alpha, beta, gammas, and deltas as operators that commute with all our logical operators. This is just a thing that you can always do for an n-qubit poly operator. OK, so the second thing to note is that the teleportation, which induces these random logical polys, when you move them across, just as we did before, will flip the sign of some of the terms in the error. So if I move these random logical operators across, what's going to happen, for example, for E1, is that this z logical is going to flip the term that is proportional to x logical and y logical because they anti-commute. And so I'm going to pick up a minus sign depending on the measurement outcome m naught. And then likewise, I can do the same exercise for E2, but now some signs are flipped depending on m naught and m1. This is exactly the same as what happens in the single qubit teleportation chain. And so what we can do is just apply the single qubit teleportation results to the logical qubit level with the assumption that E1 and E2 should be epsilon close to a logical poly channel. In other words, the logical coherence should be small. Once we make this assumption, then we can say that the logical coherent errors will not add constructively. Yeah. So the logical channel can be approximated to be the evolution of many logical poly channels, which means it doesn't constructively interfere. OK. All right, so we show that in MBEC, logical coherent errors don't constructively interfere over many rounds, which means that we have slower logical error growth with time. That's really nice. It turns out, OK, so if we go back to the challenges, we have now concluded that logical coherent errors do not constructively add over many rounds in MBEC. It turns out that if we make more assumptions on the noise model, then we can arrive at more stronger results and say something about the remaining 3 bullet points up there. So that's what we're going to do. The context with which we are strengthening our assumption on the noise model is, let's take the foliation of any CSS code, so any CSS code cluster state, where For example, in this picture, the vertices are qubits initialized in plus and measured in x, and all the edges are CZ gates. We're going to assume circuit level noise in which each gate is accompanied by an over-rotation of each of the qubits involved in that gate, and this is well motivated by 2-qubit neutral atom gates, ions, and also miscalibration of superconducting qubits and their frequencies. Okay, so we're going to assume this noise model now. And our result is that coherent errors at every gate will map to a polynoise model on each physical qubit. Okay, so to see this, since we are looking at circuit level errors, it's helpful to see the circuit. So I'm going to write out the circuit for the foliation of the 412 code so I don't have to draw too many qubits. But you can imagine that it's just a smaller part of like a bigger cluster state. Okay, so here we have our code qubits. The first thing we do is we teleport, and then we measure the stabilizers, the x stabilizers in this case. Then we teleport again, and then we measure the z stabilizers. And so by repeating this thing in the parentheses L times, we extract the syndrome information for L rounds. And then when we're done extracting the syndrome information, we do a polyframe correction dependent on all the teleportation measurement outcomes. So in this circuit level noise model, all of these dotted red circles around the gates should have this over-rotation error. But thankfully, all the errors commute through all the CZ gates, and we can just put them at the locations denoted in the solid red circles. And for these ancilla qubits mediating the stabilizer measurements, we should also get an over-rotation error as well. Okay. So we know that teleportation induces random polys, so all I'm doing here is putting that in. Something to note here is before we had all rotations about the z-axis, but because of the Hadamards from the teleportation circuit and the exchange of the role of x and z on alternate time steps, some of these errors have turned into rotations about the x-axis. And so you might be looking at this saying, okay, well, this looks pretty promising because I have a rotation about the x-axis that's preceded by a random z, and we know that this random z should flip the sign of that rotation and decohere it. And that's true. It does look very similar to the single qubit case, like the single qubit case, where you could expect for each of these dotted green boxes, you could replace it with a poly channel, an x poly channel, and a z poly channel. So the question is, can we straightforwardly apply what we know for a single qubit to this case? We're almost there, actually. There's just 2 more complications. And that's because we didn't have stabilizer measurements before, and now we do. So one of the things to consider is now we have stabilizer measurements. Before, we only had measurement outcomes of the teleportation, which we averaged over. How should we treat these stabilizer measurement outcomes? And also, we still have to consider the coherent errors on the ancilla qubits. Okay, so let's examine the first question, which is, what do we do with these stabilizer measurement outcomes? So in our foliation circuit before, we had teleportation measurements, which I'm going to denote as M, and stabilizer measurements, which I'm going to denote with S. So M's are the random the variables in the random polys, and S is just the stabilizer measurement outcomes here. Then we have, in an error correction experiment, the polyframe update followed by a decoder. You apply the correction, and then you get some effective logical channel, which also tells you the logical error rate. So in this result, we have a more stringent goal. Our goal is to show that teleportation decoheres errors in measurement-based error correction such that the logical channel of this actual foliation circuit with all these circuit-level coherent errors is equal to the logical channel of some poly error model. And we want to say this for any decoder, no matter what we choose. And another way of saying this is I want to be able to replace my physical coherent errors with physical poly errors and say and guarantee that my logical error rates are going to be the same. Okay, so just to summarize where we are right now, I'm going to denote the foliation part of the circuit with the channel E that's dependent on M and S generally. The polyframe update should only be dependent on M, which is the teleportation measurement outcomes. And the decoder, in general, should be dependent on all the measurement outcomes that we have at our disposal in order to decode. So our recovery operator, R, is dependent on both M and S. So all of this to say, we can just write down the logical error channel, which is our foliation circuit, E, composed with our polyframe update, composed with our recovery operator. And we average over all the M's and S to arrive at the logical channel. OK, so there are two facts to note here before we decide what to average over. One of them is that it's clear that the logical channel depends on the decoder because of this recovery operator R. So to make a decoder-independent statement, we should fix R for both poly errors and coherent errors. And the second fact is that we know that decoders take in detector patterns, D, and output a recovery, generally deterministically depending on that detector pattern, D. And so detectors, just as a reminder, are 0 in the absence of errors and 1 if and only if there is an error. So in order to fix recovery operator R, we should fix detectors D. But one more detail to note is that in measurement-based error correction, the stabilizer measurements in general, which I'm calling this measurement outcome S1 and S2, are not your detectors. And an easy way to see this is all of these random Z's, which are not deterministic, will flip the outcome of S, and therefore S cannot always be 0 when there is no error. OK, so it turns out your detectors actually depend on both S and M, where your detector is S plus all the measurement outcomes M on the qubits that it has support on. OK, so all I'm doing is rewriting this logical error channel we had before. Another way of writing down the logical error channel is sum over all detector patterns D. And given D, you fully define R. And then also sum over all the M's and S's that will give you that detector pattern D. OK, so if we say our decoder is oblivious to whether we have coherent versus poly noise, this should be the same for both poly or coherent errors. So at the end of the day, what we really need to make a statement about is this part of the channel, which is averaging over all the M's and S's that give the same detector pattern. Can we say that for every detector pattern D, this channel is equivalent for poly noise and coherent noise? And this does, in fact, work out. And so since we are able to say this about these data qubit errors, we have concluded that circuit level E to the I theta Z errors on data qubits are essentially poly errors. OK, so the thing that's left to deal with is the E to I theta Z errors on the ancilla qubits, and then we're done. So this last detail, ancilla coherent errors are decohered. So we've shown that all the errors on data qubits are poly. What about these ancilla coherent errors? So here we have data qubits that are undergoing poly channels, thankfully. And then we measure the stabilizer. And this ancilla qubit can have some rotation error on it before we measure out. So let's define perfect projectors. So let's ignore the error for now. If we had perfect projectors, pi 0, for example, would project you onto the +1 eigenspace of the stabilizer you're measuring, or the eigenspace where you measure that S to be 0. And pi 1 is the perfect projector onto the -1 eigenspace of the stabilizer. So this blue dotted box actually results in imperfect projectors on the data qubits. So the form of this blue box on the data qubits is actually what I'm going to denote as pi tilde 0, which is cosine theta, where theta is the rotation angle of the ancilla qubit. The cosine theta, the correct projector, plus I sine theta, the wrong projector. And then likewise, for if you measured S equals 1 in that blue box, then what you're actually doing is this imperfect projector, pi tilde 1, which is cosine theta, the right projector, plus I sine theta, the wrong projector. So we know that before any stabilizer measurement, due to data qubit poly errors, the state is either S equals 0 or S equals 1. So it's either in the +1 or -1 eigenspace of the stabilizer you're measuring. And it's not in, importantly, it's not in a superposition of them. So if we apply imperfect projectors, let's say, for example, onto the +1 eigenstate s equals 0, then the only term that survives, say, after this imperfect projector pi tilde 0 on s equals 0 is this term cosine theta s equals 0. And then the other imperfect projector only keeps the term I sine theta pi 0 s equals 0. OK, but the main important part here is basically, one, that the post-measurement state remains the same. It's still in the +1 eigenspace of the stabilizer. And so therefore, we can conclude that this ancilla coherent error on the stabilizer measurement can be modeled as the correct measurement with probability cosine squared theta, and the incorrect measurement with probability sine squared theta. So essentially, this coherent error on the ancilla, we have nothing to worry about. It can just be measured as a stochastic measurement error. So we've shown that these eta I theta z errors on the data qubits are Pauli, and we've now shown that these eta I theta z errors on the ancilla qubits can be modeled as essentially if you took that coherent error and twirled it and applied it right before you measured the stabilizer. OK, so our result is that we've shown that coherent errors at every gate in measurement-based error correction directly map onto a Pauli noise model on each physical qubit. So this straightforwardly works for any foliated CSS stabilizer code and for the foliated XEZX code. And so let's revisit the challenges of coherent errors. Now that we know that our errors directly map onto a Pauli noise model, we know that there exists a constant threshold theorem applicable for these eta I theta z circuit level errors in measurement-based error correction. Before, there's potentially this large difference in logical error rates for Pauli versus coherent noise. And now we guarantee that the logical channel of these circuit level error, coherent errors in measurement-based error correction is equal to the logical channel of a Pauli error model. And so as a result, we can exactly and efficiently compute the logical error rate for these errors in measurement-based error correction. And so all of this to say is that these challenges of coherent errors are not actually challenges in measurement-based error correction. So our work adds to other pros of measurement-based error correction, which is inherent mitigation of leakage and qubit loss, because you're always teleporting to a fresh new set of qubits. Higher thresholds and code symmetry preservation for biased noise models. And now we know that it also inherently twirls coherent errors, allowing for efficient QEC benchmarking of circuit level coherent errors and preventing quadratic error growth. OK, so this is a summary of the results we've shown and all the challenges that we've aimed to overcome with this work. I would say that an outlook is that teleportation can introduce these random polys, which are not just a feature, but things that you can use to your advantage, and can introduce this intrinsic randomized compiling in your protocol. So yeah, that's all.
Thanks, Katie, for a great talk. Do you have any questions? Yes.
So yeah, thanks very much. That's really cool. So I suppose I'll restrict myself to one question for just now. So in the second part, when you were talking about the logical coherent errors,
Right.
There's this mapping where you have physical level coherent errors that map to some logical level coherent error. And as I understand it, you said, look, we conjecture that the coherent error at the logical level is small.
Yeah.
But I'm wondering what you know, if anything, about how the size of the coherent level of error at the logical level is connected to the coherent error at the physical level.
Yeah, that's a good question. So if you were to truly calculate out what the resulting logical coherent error is, what you would need to do is, given all these physical qubits with physical coherent errors, put them through a stabilizer measurement, which in general is going to be difficult to compute. And furthermore, yeah, it's only half of the stabilizer measurements as well. So at this moment, I can't say anything about the direct, how much the coherence will be. If I have this given physical coherent error, how much will the logical coherent error be? I think it's closely tied to the distance of the code.
Yeah.
Yeah. Yeah.
Maybe I just understood when you talk about the over-rotation of the two-qubit gate,
Yeah.
you're modeling that as appending these two single-qubit rotations.
Right.
But it could also be like a small, e to the I d theta zz could be like your
Right.
over-rotation.
Right.
Does that still work?
Yeah, that's a great question. So we didn't go through the detailed analysis of that, but my feeling is like even a single qubit x, if you have this e to I theta z1, z2, for example, is going to flip the sign of that. So it could not be a problem. Yeah.
Yeah, so your analysis is kind of based on these correlated schemes.
Right.
The way you went through it, but the result, you think, is applicable to measurement-based error correction in general, but it isn't from a correlated scheme. So, well, I guess, is that true? Like, can you say something about measurement-based error correction in general?
Right, yeah. So I think that's a really great question. We know that for the RSG cluster state, it's isomorphic regardless of what you've interpreted to be your foliation direction or your time direction. And so that gives me hope that like this is really not specific to the foliation picture. But we haven't gone through detailed analysis of non-foliated instances of measurement-based error correction, but I think that's a really good, interesting line of work.
Still about the error model that you're assuming. Maybe
Yeah.
I missed it. Did you say anything about, because here you have this CZ gate,
Yeah.
and you have also e to the I theta z, so they
Yeah.
commute. This was
Yeah.
one of the parts of your analysis. What happens if the coherent rotation is actually about the x-axis, for example?
Yeah, so what if they don't commute? Yeah, so I think the analysis gets a bit trickier. So the thing that is annoying about coherent errors and analyzing them through Clifford circuits is that you have you have superpositions of polys that you have to push through Clifford circuits, which exponentially gets more and more expensive to keep track of. And so when I was doing this analysis, I kind of struggled with a tractable way to deal with errors that didn't commute through every single gate. So we ended up with this result instead. But yeah, I think.
So I sort of note why is it I'm asking such a question, because if everything commutes
Yeah.
towards your gates,
Yeah.
essentially what you're saying is that your teleportation, your error correction circuits are all perfect.
I don't think that's necessarily true. Yeah, no, that's fine. If they commute through your gate, then your
I
error.
can essentially pull all the things to before my error correction or my teleportation, so I just have input errors, and then everything else is sort of perfect.
I'm not sure. Maybe we can go through what you were saying. Sorry. Yeah, so I guess if we were to kind of pushing through, I mean, I don't think it necessarily means that all your qubits are perfect. I don't know if I'm misunderstanding your statement.
I can think of it as perhaps input errors only, followed by a...
Oh, input errors, I see. I don't think it's necessarily like that because, I mean, with these, like if you are doing rounds of stabilizer measurement, like I don't see how you can push some of these errors. Like I only drew one round of stabilizer measurement, but if I were to do this again and I had some e to I theta z errors, I'm not immediately seeing how you can, yeah, I'm not sure. Maybe I'll hold off on saying anything before, yeah. Yeah.
Thank you for your interesting talk. Can you go to the slide comparing coherent and Pauli errors, showing the
Yeah.
causal non-linear dependency on T?
So is this at the beginning?
Yeah,
Yeah.
in the beginning.
Okay. Yeah.
Yeah, the graph.
Is this one?
Yeah, this one.
Yeah.
I was just wondering how the result will change if we consider randomized theta values. I mean,
Uh-huh.
in practice, it should be an arbitrary
Mhm.
So I think it works like a random
Randomized compiling.
like random work.
Yeah. I've talked to some people, like especially with the neutral atom platform and stuff, and like you can have thetas that vary. Some of them can be negative, some of them can be positive. In general, what they see is like the non-trivial case is like the biasing of a little bit not centered around 0. And that's what you're worried about, because if it's already centered around 0, then you aren't worried about the accumulation of these coherent errors to begin with.
Yeah, so I thought that if it is
And so-
if it is a complete random work, then that dependency might be not quadrature but linearity.
Yeah. I had another plot basically at the end of the second section, which what we're doing is we assume like a biasing towards like a positive theta, and then we randomize around that that angle. It was like the second one. I don't want to click through all of it, but but yeah. We're considering the case where it's not centered around 0. Yeah.
Then it might be a very naive approach, but if we can identify such a bias on the coherent error,
Right.
then what if we can just rotate a little bit less than the desired value?
Yeah, I mean, like, my feeling is that the experimentalists already work very hard to like limit this kind of error already. So they do things like dynamical decoupling to basically get rid of as much of this biasing as they possibly can. But even that has like its limitations on like the precision of their clock, which they're used to do this dynamical decoupling. Because if you do it exactly half in the middle of your accumulation of your error, you cancel the error out exactly. But in general, this is not always what you're able to achieve. Yeah.
One of your criticisms for randomized compiling is that you have to do more gates. And so
Right.
I guess you're trading off coherence, like you can reduce the coherence of
Right.
the code, but you increase the overall level of errors
Right.
by doing more gates.
Right.
Is it fair to say that this procedure maybe has a similar feature because you have to do these CZs?
I see what you're saying. Yeah. So I think that the way I would kind of think about this work is it's like a cool consequence of a feature already intrinsic to measurement-based error correction that we were going to do anyway. So for example, in qubits that experience a lot of loss or leakage, you're going to want to eventually replace all your qubits at some point in the computation. And so that's going to involve teleporting your logical information. So you can't really get around not doing this. You can't just have like a chip with qubits living on it forever. So if you're going to do this anyway, this is also a nice consequence of teleporting. Yeah.
So in the first explanation you gave of the 1D, the simple 1D physical level teleportation,
Right.
when you were considering rotation about a fixed axis like X, Y, Z,
Right.
you sort of got to the point where you'd sort of convinced me, oh, it's exactly like doing a Pauli. And then when you said E is now a general
Yeah.
thing, this ET is now general,
Right.
you're correcting, you said, well, it's actually approximately a Pauli up to epsilon to the 4th correction.
Yeah.
I'm just wondering if you could give a flavor for where the epsilon to the 4th comes from.
Yeah, okay. You know what? That's I'll try my best. So essentially what happens is in those other examples where you can tractably write out the Pauli channel, what happens is you can do a sharp cut of there are no coherences between these two sections of the chain. But when you have general errors, for example, just take e to the I theta x plus z on each of these e's, no matter where you cut the chain, you're still going to get coherent interference between any two time steps. And so it's impossible, like when you cut it up and write it as a composition of Pauli channels, which has no coherent interference between them, you are making approximations because that is not actually the channel. And so basically where this epsilon is coming from is what we do to, so I guess what I see the randomized compiling as like a very bad approximation of the actual teleportation chain. It's like if you truncate it at order 1, where you just take the diagonal terms of the channel. But then as you add in more interference with the previous time step, or maybe the time step before that, you gain more powers of epsilon in your accuracy, and that's what allows you to make these tighter and tighter bounds. Yeah.
Any further questions for Katie? If not, thanks again.